Lisa. So do you see my screen? Right. Okay, so hi again
yes,
for,
can see.
yeah, okay, perfect. So hi again for those who have seen my other presentation earlier this morning. Hi to the others. I am Léni Goff, currently a postdoctoral researcher at the University, Napier University of Edinburgh. I will present you here a work I have done with my former colleagues Alexandre Coninx and my former PhD supervisor Stéphane Doncieux from Paris, and with my current collaborator Emma Hart about on the pros and cons of neuro-evolution with evolving topologies on novelty search. So this work falls into the context of evolutionary robotics with neuro-evolution. So we have a robot, like for example, the epoch here, which is controlled with the neural networks, and we put it in an environment, and the goal is to optimize the controller with evolution to find the best behavior. In this work, we are interested in comparing evolving topology of the neural networks with novelty search with more simple fixed structure neural networks with novelty. The question we ask here is, does the advantages of evolving topology worth the complexification of the algorithm itself? For example, one of the drawbacks of using evolving topology is that you have various size of genotype. You can have different size of genotype, and that prevents the use of a very powerful method like CMIES. The expected advantages to use evolving topology with novelty search is mainly two. This is these two aspects we have investigated in this paper. First, we could expect a better uniformity of exploration. Indeed, in the work of Doncieux and its colleague, they don't study with evolving topology, but they show that novelty search novelty search tend to do a uniform exploration of the behavioral space of the robot. So here, if you have a genotype with a great degree of liberty, you can expect to have a higher diversity in terms of behavior and therefore a better uniformity of exploration. Also a faster bootstrap. What we mean by bootstrap is what is going on at the first generation, first evaluations. And here, for example, on the graph you can see on the right part of the slide, here we have a very fast bootstrap, and this is a phase in which we can, the phase before going into convergence. So we could expect a fast bootstrap with evolving topology because, for example, with the case of augmenting topology with NEAT, for example, we start with small neural networks, and then they are easier to optimize. But why studying this question exactly? This very detailed and precise question. It all started with this paper, in a very good paper of Lehman and Stanley of 2011, in which they introduce a new way to do evolution, in which you replace the classical goal-based fitness function by an objective function which rewards the novel individuals, which is called novelty search. I tested this on two challenging tasks, a navigation task and a walking robot task. However, they directly propose this method by using NEAT, a method they introduced 2 years before. So we could wonder if evolving topology is required to use novelty search to have the full potential of novelty search. Of course, there is other papers which have studied novelty search and more broadly divergent search methods, like the work of Tarapor and its colleague about comparing different encodings with mapelites and other divergent algorithm. The work of Moret and Doncieux about comparing different methods to encourage behavioral diversity in evolutionary algorithm, and the very complete empirical study about novelty search by Gomez and its colleague in 2015. In all this work, they are not studying the question of evolving topology as a central question, but there are some side results in this paper, which shows that evolving topology is not always the best choice in terms of divergent search when you want to do divergent search. So to compare evolving topology against fixed topology, we decided to use a direct encoding we call DET for direct encoding for evolving topologies, proposed first in the publication of Morin and Doncieux in 2012, in which simply we have in which all the encoding is relying on 5 mutation operators, adding a neuron, removing a neuron on its connections, adding and removing a connection, and polynomial mutation on the weight. All these mutators have a mutation rate, so a probability to be applied. You can see on the bottom table the value we use for our experiment. With these values, you have augmenting topology behavior in the algorithm, like NEAT. So here we compare this with 2 fixed topology networks, so classical fully connected feed-forward neural networks and Hellman networks, in which you extend the feed-forward neural networks with an additional layer called context units, in which each node is recurrently connected to itself. We use different sizes of each of these topologies, so 2 sizes of feed-forward neural networks, one with 4 hidden neuron and one with 16, and 4 2 feed-forward, sorry, and 4 Hellman networks with 4, 16, 2, 8, 16, and 64 hidden neural networks and the same number of context units for each. And we use polynomial mutation to mutate the weights. We conducted experiment on 2 task domains, a 2D maze navigation task with a robot equipped with 3 proximity sensors on the front. The black dots indicate the starting position, and a 3D walker task with 3 different robots, with a small robot with 2 degrees of freedom on each leg and a bigger robot with 4 degrees on freedom on each leg on the intermediate one. In this task, we put the robot in the middle of a squared arena, and the robot move and have to go as far as possible. In this work, we're interested only in novelty search. We are conducted pure novelty search, pure exploration. So there is no goal here. What we expect as a final result is to have a population that cover all the space of the maze for the navigation and of the arena in this case of the walker. So the behavioral descriptor we use here to compute novelty search is the final position of the robot. We use 10,000 generations for the 2D maze and 4,000 generations for the walker. We have 400 individuals in the population, fixed evaluation time, and 10 replication for each experiment. We use a classical genetic algorithm with tournament selection and no crossover. To compute, to have a measure of the uniformity of exploration and of the coverage of the behavioral space, we use a measure based on the Jensen-Shannon divergence, which is a method to compare two probabilistic distributions. So here we compare the perfect uniform distribution in the behavioral space against the actual population distribution of the behavioral descriptor. So as first results, we have plots that show the exploration uniformity over the generations. For the hard maze and the multi-maze, the DET, so the evolving topology, is indicated in green. You have two zoom on the plots, which is one zoom on the convergence and a zoom on the bootstrap, so on the first generation. So the first thing we can see is that the best method, so the best algorithm to reach uniform expression is not DET. For the hard maze, the best one is Hellman network with 16 hidden neurons. And in the multi-maze, there is DET on the elementary network with 32 hidden neurons are quite on the same level. Also on the bootstrap, we can see that on the hard maze, DET is the slowest to bootstrap, and this on the multi-maze is quite slow to bootstrap as well. It's not the slowest, but is quite slow. Same results, similar result on the 3D walker. So here again, you have DET on green, and we can see that is the worst one for the in terms of uniformity of exploration. And on the zoom of bootstrap is slower with the 2 degrees of freedom per leg robot, but I have the same speed of bootstrap with the other robots. Here, the best method is the Hellman network with 32 hidden neuron. It's not significant on all with all the robots, but it seems to be the one to use for each of the tasks. So as second results, we have plotted the number of connection and neurons inside the neural networks evolve with DET, and you have in the table also the number of neurons on connection for the fixed architecture. So what is very interesting here is to see that the best networks, which are here the Hellman network with 16 and 32 hidden neurons, have much more connections than the neural networks evolved by DET. So even if in this case, DET don't reach the best uniform exploration, it's interesting to see that he is able to reach satisfactory results with a less complex network. So same results for the 3D walker. This is even more significant. The best network, fixed network was the Hellman network with 32 hidden neurons. They have way more connections than the one evolved by DET. So to conclude this presentation, some pros and cons for evolving topology. So here for the special case of augmenting topology. So augmenting topology converges to simpler architecture, which is a very nice feature. And also still the automatic design of the neural networks is interesting. However, augmenting topology is slower to bootstrap in the task we have tested here. Sorry, and augmenting topology does not guarantee always a better exploration or diversity. Some interesting side results. So as expected, the Hellman networks, the recursive networks perform better in terms of exploration than the feed-forward, which is expected because recursive neural networks are able to have a short-term memory thanks to their recursive connection, recurrent connection. And also, the best network architecture is not necessarily the most complex. So what we have seen is that you have to reach a certain complexity to be able to have interesting behavior and diverse behavior. But if you augment too much the complexity, you have a decrease in terms of diversity of behaviors. So this study, of course, is limited. We have tested this only in 2 task domains, maze navigation and working robots. So these results are very specific to these tasks. And also, we didn't conduct a study on the hyperparameters values of the DET methods. So maybe we could tune the parameters to have a better uniformity of exploration. So thank you for your attention, and that's all for me. And if you have some questions, feel free to ask.
Great, thank you. If anybody has a very, very quick question, we can take it. Otherwise, we'll move the questions over to the chat.
Okay, great. Thank you.
Thanks. Okay, and now we have our final talk of the session.